שלום. כמה טוב שבאת.
כן, אני קלטתי לא, כולם מודעים להרצאה הזאת, פשוט...
רגע, אתה אחראי להדליק משהו, נכון?
ביירון, עניינים.
לא, או שזה לא עובד. הכל דלוק?
רואים אותך ב...
כן, רואים אותי.
אני יכול להפעיל מיץ, אין לי בעיה.
יאללה, תפעיל מיץ, למה לא? אל תדאג. אני אתן לך עוד הערכה לזה שהגעת. איך הלך בבוחן אתמול? לא משהו?
היה נחמד.
היה נחמד, אוקיי. כבר טוב.
אפשר להתחיל בינתיים סטרסים.
כן?
ממש מעכב, כן.
לא, אתה לא מעכב. מי זה מעכב? אני ואתה פה.
לא, כן.
הכל בסדר, תדליק את הזה. אם זה ייקח עוד איזה 5, 4, 3, גם 3-4 דקות זה בסדר?
כן.
נתחיל. אל תרגיש לא בנוח שאתה תהיה פה לבד.
לא, רציתי...
אני די מהר אשכח מקיומו של הקהל ואני אכנס לתוך הפיזיקה, יהיה בסדר. אני פשוט שונא להעביר הרצאות בזום. זה הרגשת תפוקה מאוד.
לא הבנת, אני... מסיימים?
אין שם אף אחד. כולם טוב.
יש את זה.
הכל טוב.
כולם
יאללה.
טוב. יאללה, מעולה.
תרשום את שמך. לא, כדי שאני לא אשכח. וואו, את שלי. אתן לך נקודות בונוס בסוף הקורס. לא צוחק. יש פה עט, הנה יש פה עט. זה כותב. ככה. Good morning, everybody. We are starting our lecture. Despite the Byron storm, physics must go on. I remind you first where we ended, not yesterday. Yesterday was a quiz, but was on Monday. All right, so just a sec. The idea is that Einstein model was disappointing at low temperatures. What we managed to do is not big, but divide, is to correct those assumptions made by Einstein. But again, we start with three-dimensional lattice. We have fluctuations. We have some sort of fluctuations, but we do not throw away all the correlations and the mutual motions of different particles. The idea is, it's not that every single particle over here oscillates on its own. Every single particle is doing something together with all the different other particles. Right. Now, when we do all of this, and we diagonalize, so we build a Hamiltonian, we diagonalize the Hamiltonian, eventually we obtain that the Hamiltonian was of the form m, a summation I goes from 1 to 3n of zi dot squared plus d, or let's write it down as omegas, omega I squared zi squared. So we got a bunch of harmonic oscillators. The only thing that those zi's are not representing real position of real particles. Right? I remind you that z vector was a multiplication of a vector xi by some metric s. Okay. So what was this vector xi? Those x's were the fluctuations around a minima of a very general function x1, 1, x1, 2, x1, 3, till x and 3. So we had a huge potential energy of all the different positions, of all the different degrees of freedom. We found a minima. X's are fluctuations around this minima of all the different degrees of motion. Moreover, we took a second derivative, aij, was du of dxi dxj. So we have this huge matrix, which was 3n by 3n, 3n by 3n matrix, right? And we said, if we take this matrix, we find the eigenvectors of this matrix. Out of these eigenvectors, we build an S matrix. Great. Impossible to do. Then we find the minima over here, multiply this xi by this s, and voila, we have those new coordinates. We call them zi's. We had a name for them. Those are phonons. Okay. And they are fluctuating, but it's impossible to find their positions. So in principle, Einstein right. It is indeed a bunch of harmonic oscillators to some extent. The problem is that the harmonic oscillators are not single particles, but some coordinate that describes a specific position of this and that particle. Okay. problem number 2, not just the position, are what all these Wi's. In Einstein model, all the W's were exactly the same. For any I, Wi equals W. That's it, you solve everything, you have one single W, and that's corresponded to what? To the partition function is just Z1. You have to compute the partition functions of one single particle and take it to the power of 3n. In Debye, it's different. So we don't know what those Wi's are. Moreover, we know that those Wi's are different because they came from this huge matrix A somehow. We don't know what they are, but we just know that they exist. Okay. So we don't know. What then can we do for the partition function? So this is the sum of independent particles. We call them phonons. Those particles have kinetic energy and harmonic potential energy. They are independent. So we can use factorization, but the factorization means we have to go from I goes from 1 to 3n of zi. And this zi is going to depend on omega I. So that's the problem. Not just everything is identical, it's not identical, and we don't know what those omega i's are. Okay, that's important. The next step that we suggested, so that's the problem. This is what we need to solve. We need to find omega i's. For each omega I, we need to compute zi omega I, and then we'll have the partition function. The moment we have partition function, we can take a derivative of this guy, a derivative of that guy, etc., etc. Okay, and then out of this, we can compute the appropriate partition function. Okay, so how we started to find the partition function? We did the following thing. Said we cannot find the omega i's explicitly. Why? Again, it's related to this huge matrices S and huge potential energy, which depends on 3n. This huge, enormous matrices. 3n by 3n. Think about n as always as an order of Avogadro number. So it's 10 to the power of 23. Think of diagonalizing a matrix of 1023 by 1023. Impossible. It was impossible when Debye tried it, and it is impossible even today. And probably it's going to be impossible tomorrow. Now, next thing is to say, well, look, we don't really know what omega i's are, so we need to introduce physical intuition. The moment I say physical intuition, what I mean, some assumptions. So any real physical system composed of many particles, not that the stuff that you've been taught on classical mechanics, nautical mechanics, electromagnetism, you have a single particle, you have a wall, very, very simple, nice. So any system is not neat, it have a bunch of degrees of freedom, and you always need to know or understand or maybe assume what's important. Okay? So when I'm saying, let's introduce physical intuition, I'm saying, let's try and impose something on the system. Okay? Great. So what we are doing, we suggested the following approach. So remember, eventually we need to compute the free energy. Free energy is minus 1 over beta log of z. In our case, z is a multiplication of a bunch of partition functions. When you apply logarithm to multiplication, it turns to a summation over different logarithms. So f in our case is going to be minus 1 over beta log of pi I goes from 1 to 3n of zi omega I, and this goes to minus 1 over beta, a summation I goes from 1 to 3n of log of zi omega I. Again, well, nothing difficult, but in order to compute this integral, you need to know all the omega i's. The physical assumption comes, well, let's assume that omega i's somehow, maybe, they're almost dense. Okay, so we need a spectrum of all those omega i's, right? So if you look omega i's have to be positive, because positive and negative are exactly the same in a four-harmonic oscillator, because you have omega I squared. So we look on the spectrum of possible mi. So we'll have, if we'll sort them out, up z1, z2, z3, z4, we have omega 1 and omega 2 and omega 3 and omega 4, etc., etc., etc. The problem is to find the spectrum. Physical assumption comes and says, what if the spectrum is actually continuous? Okay. So instead of having those discrete omega i's that have to be, we assume that those differences over here are very small. So tiny. This is our physical intuition. Delta omega goes to 0. If delta omega is small enough, okay, then we can say, well, we have, instead of discrete spectrum, we have a continuous spectrum. Okay? So, and if you have a continuous spectrum, instead of the summation, you have to produce an integral, right? So this guy goes to an integral, have minus 1 over beta, that stays exactly the same. I still don't really know what are the lower limit of my integration and what is the upper limit of my integration, okay? But I know what's going to be inside, at least partially. It'll do it. And what's going to be inside is log of z of omega, right? Z depends only on omega. Omega is now a continuous function somehow, going from I don't know what to I don't know what yet. Okay? And we'd say, oh, let's call here d of omega. Now, that's not true. Why? Because when you go from a discrete spectrum to continuous spectrum, you need to introduce the density, right? So here have to come some d over omega density of omega, right? So I need some density function of omegas, okay, that I don't know what it is yet. Okay, so again, the story. I don't know what the omega's i's. I make a physical intuition that they are somehow dense, right? They are dense, so I have a discrete, not a discrete spectrum. I have a continuous spectrum. I have a continuous spectrum. I can make this summation into an integral, but I don't know what the density. I have to include the density. Anytime that I go from a sum to an integral, I have to include the density. Okay? It's always like that. If you want, I can explicitly show it to you, but probably seen it already. So now it's 3 questions. Lower limit, upper limit, density of omega. It sounds that I'm not making almost any progress, so some cosmetical issues, summation, integration, but there are very hard questions that are still inside. So instead of a specific explicit spectrum, I need a density. How I find the density, I still don't know. Maybe it's related to this extremely large matrix, etc., etc. But this is actually progress. And this is where my physical intuition comes extremely handy. What are those? So let's think about it for a second. So we're saying we have phonons. And each phonon is described by a harmonic oscillator, right? So if you look on some specific Zi, so phonon number I, Zi, we know that the energy of this phonon is what? Is 1/2 the mass of zi dot squared plus omega squared zi squared. Okay. This is the phonon. And omega describes the oscillations of those phonons. Okay. Think about it. So if we have a harmonic oscillator, the oscillations describe what? The oscillations of harmonic oscillators are cosines or sines, right? That's it. But it's not that. There is no dissipation over here. So if I have indeed harmonic oscillators, what it tells me that each harmonic oscillator describes a specific wave that lives inside a system. This wave have a frequency, omega I, and it does not die off. That's very important. I take a particle, I connect it to a spring. I don't have any friction. So what happens? I pull it out a little bit, and then the spring starts to oscillate, right? And it will oscillate forever. This you know from regular Newtonian mechanics. If the spring is oscillating and I'm not infecting it by friction, it will continue to oscillate, continue to oscillate, continue to oscillate. So each harmonic oscillator describes a wave that lives inside a system. Not just a wave, standing wave. So it's important. What we now see that our description is that instead of taking off single particles that are doing something, we're describing the whole system as a bunch of standing waves that somehow live inside the system. And all those standing waves absolutely do not interact. Why? Because the energy is a sum of different energies. So I have a wave and it's doing something and it continues to do something. It might be affected by the temperature, yes, okay, but it's still a standing wave. All right, so if we have a standing wave, maybe I can find the density of omegas by making an analysis of what? Making an analysis of how many standing waves I have inside my system. And that's it. So the idea is you've done it with mass. How you find the mass density? Remember Physics 101, Classical Mechanics, even not analytical class if you've been taught it in physics department. Eli Slutskin, if you want to be taught this in engineering department, who knows? He's teaching there it's right now, but the idea is the same. If you have a mass, right? If you have a beam, okay, and you know that in this beam, the density of the mass is rho of x. This is x, and the density of the mass is rho x. Now, the simplest example, when the mass is uniformly distributed inside the beam, but it does not have to be that way. We know that the total mass, m, okay, is what? As an integral, this is 0, this is L, okay, an integral from 0 to L of rho x dx, right? This is total mass. We want to find, okay, but what is the mass density? Okay, what is the mass density? Which is rho of x. So usually I know what is m, I don't know what is rho of x. Oh, the other way around. I usually know what's the density, and this is how I find the m. But oh, what if I have it opposite, upside down? What if that I know what is m of x, right? I know what's m of x, somehow. And m of x is just an integral from 0 to x, rho x prime dx prime. So if I know how much density I have in the beam, how much mass I have in the beam as a function of s, I can find the density, I can find rho of x. So rho of x dmx to dx, I take the derivative of this guy, is just whatever stands inside, simply rho of x. So I know how to find mass density. I need just to calculate the mass as a function of x, all right? right? And take a derivative with respect to this x. You compute the total mass, you take a derivative, this is your density. What if we can use exactly the same idea to find how many standing waves we have inside the system? Or more properly, what is this density d of omega? The idea is as follows. If I can compute, here, right? If I can compute the number of standing waves we call it omega of omega, that when omega is smaller, omega prime, than omega. So what I'm doing, I'm asking, what is the number of standing waves from here to here? If you think about the discrete spectrum, it's easy. You just have to count all the different omegas that are inside. Okay, so you count their numbers, and then you make a derivative, right? So if you take this omega of omega, which is your mass up to a specific point, this is the mass, the total number of waves, standing waves, up to a specific omega, and you take it with respect to d omega, you'll get your density of omega. And this is a progress, right? Why it's a progress? It's a progress because we have now an idea of how to find this. But you say the only thing that you need to do is to count the numbers of omegas up to a specific point. Moreover, it's not just some arbitrary omegas. Those are omegas that are standing waves inside your system. So you have, first of all, this is the algorithm, this is a prescription of finding the omega. First of all, understand how many standing waves you have to a specific omega. All right? The moment that you know it, take a derivative of this number, and you get the density. Okay? So what we need to do is just to count the number of standing waves, because we understand that each omega is a standing wave. If we know how many standing waves we have up to a specific threshold, okay, that's enough. This is going to be omega large of omega small, take a derivative, and you're done. And the standing wave is crucial here because we know a lot about standing waves. Okay. So let's do it first as if I have a one-dimensional system because it's easier, and then we'll go to 3 dimensions. Why this equals exactly to the density? You understand this on the level of the mass? It's exactly the same. Okay, so because the integral from 0 to omega of d omega prime d omega prime, it equals to what? It equals to the total numbers of omegas in this limit. Okay? This is exactly omega. Think about it, it's exactly like the mass density, nothing more. But instead of writing m, I'm writing omega, that's it. Right. Okay, so now we need to find omega of omega, and we know that those are described by standing waves.
Stas,
Okay, yes.
could you repeat why are they standing wave? Why isn't it just any general wave?
No, because it's harmonic. Any general wave will eventually dissipate, right? If you take a wave and it's not a standing wave, it's eventually dissipate out of the system. This is something that persists for extremely long amount of time. Alright? That's it.
So they don't dissipate.
They don't dissipate. Do we have friction over here? In this perspective, you don't have any friction. They do not dissipate. They're always there. The only kind of waves that survive in the system, eventually standing waves that somehow satisfy boundary conditions. Otherwise, they will go away. Okay?
Thank you.
Okay. So what we are going to do first is counting number of standing waves. we first do it in one-dimensional system. It's easier, and then I will show you how to do it in 3 dimensions. Okay? First in 1D. Okay, so let's assume this is my system. It's one-dimensional. It's the size of the system is L. So what do I know for standing waves? For standing waves, I know that L divided by lambda, it's the wavelength, divided by 2. What is lambda? This is the wave length. Okay? Equals to what? It's a number. Special n. N. N equals to 1, 2, 3, 4, 5, not 1.5, not 1 1/3, not 1 1/2. It's always waves, standing waves. They do, for example, something like this. Depends on your boundary conditions. Or they do something like this. Okay? Or they do something like this. Okay? So you have standing waves, and you know that the different standing waves, how I find the different standing waves, depends on the number n, which is discrete. It has nothing to do with quantum mechanics, although the quantum mechanics discreteness comes exactly from the same origin. Right? Why there is discreteness in quantum mechanics? Because you have wave functions and you treat it as a wave, and the wave have to satisfy specific boundary conditions, Sturm-Liouville, blah blah blah, and you have this discrete numbers. Here, don't care about quantum mechanics, we just look on the classical system with n. And this n is 1, 2, 3, 4, 5, 6, 7. Okay, so this, we know, this will help us to count wave, because somehow we understand that we just need to count specific n's, and that's it. Okay, so what do? We do the following thing. So first of all, I don't want to operate with lambda. I want to operate with k vector, okay, or wave vector. Remind you, what is k? K is just 2 pi divided by lambda. Okay, so what we obtain from this, what we obtain from this guy, is that let's substitute it here. So we have L multiplied by 2 divided by, instead of lambda, I have 2, so out of this is lambda equals to 2 pi divided by k. Okay, so here I have 2L divided by lambda. Instead of lambda, I write 2 pi divided by k equals to n. And I obtain a very nice expression that you probably seen in other classes. K, this k vector, equals to n L divided by pi.
And pi over L.
And pi over L. Ah, yes. Sorry, you're absolutely right. N pi over L. Okay. This will help us to count waves. The next step is to say, all right, remember, what is the idea? The idea is to count the number of waves that survive in the system up to a specific omega. Okay, this is what we want to compute. Right. This is the total number of waves. All right. Now remember, omega somehow depends on k due to a dispersion relation. Omega depends on k. Dispersion relation. But we don't know what exactly this dependence for now, but there is some dispersion relation omega k. All right, so we can say that omega is actually large omega, is omega that depends on a specific k. So in order to count the number of standing waves up to a specific omega is to count the number of standing waves up to a specific k. Okay? So we pick up k. We pick up a specific k. How many waves there are in the system that have a k vector which is equal to k or smaller to it? So count all possible k star, k prime, such that k prime smaller or equal to k. But all the different k primes, so all k primes equals to n pi divided by L, n prime. So when we say count all the k primes such that it equals to smaller than k, it is exactly as if what we count all the n primes such that they are smaller by a specific n. So n prime depends on k prime, and n depends on k. So in order to count the standing waves, I know each standing wave has a specific number, full number, regular number, 1, 2, 3, 4, 5. So I not need to find, well, what this specific k is. I need to find the number of standing waves with k lower than the large k, which actually says, okay, pick your k. For this k, find the appropriate n. It's going to be 1, 2, 3, 4, 5, 6, 7, whatever. It's going to be a specific number. You pick this one, great. Now you ask the questions. What are the numbers that are lower than this nk? It's easy in 1D. So for example, n goes from 1 to 2 to 3 to 4. So if I pick n equals to 5, right? So the total number of waves, standing waves, with n prime equals or smaller to 5 is how many? Those I have. I have 1, 2, 3, 4, 5. Just 5. Okay? That means that omega of k equals to 5. For this specific k, for which n equals 5. So it's easy. Now we see, at least for this one-dimensional case, the number is just, okay, pick up this n, describe this n in terms of k, and then count all the different numbers that are smaller than this number. what is the number of different n prime such that n prime is smaller or equal to what? To what was the relation? We remember what's the relation between k and b. K equals to n pi divided by L, right? So n equals to what? K L over pi. What is the number of different n primes such that n prime smaller than KL divided by pi? Remember, n can get 1 and 2 and 3 and 4 and 5 and 6 and 7 and 8. So this number, it is just KL divided by pi. You count them, it's easy. You go and count 1, 2, 3, 4, 5 till you reach KL divided by pi, and then you stop. Right? So we found our omega of k. This omega of k equals to KL divided by pi. So for one-dimensional system, we found the number of waves, okay, up to a specific omega. The only problem is, okay, what is d omega is going to be? D omega, it always d omega to d omega small. In our case, it is d omega to dk, dk to d omega. And for 1d, d omega to dk is what? Is L divided by pi. Okay, it's L divided by pi multiplied by the dk to d omega. It's a huge progress. Why it's a huge progress? Because we found the density. The only unknown thing in our density over here is this guy. What is dk to d omega? So your physics have to describe, eventually pin it down, what you need to assume. What are the crucial physical assumptions inside your system, where the physics comes in. And in coming in now, at least in 1D, in how k, the wave vector, depends on omega. But to do that, you know how to apply whatever you have learned in the class of waves or in different other classes on optics, is that the dispersion relation. You know the dispersion relation, you know the dk of d. So the density of states is completely defined by your dispersion relation, at least in 1D. Right? Absolutely, completely defined. You know something about the dispersion relation, you know the density of states, because that's the only thing that lets to find. How you know the dispersion relation? You can measure it. You can include your knowledge out of somewhere else. You maybe can compute it sometimes. You can assume what the dispersion relation is. So there are many ways. You don't need to diagonalize the matrix now. You know that everything pins down this guy. Right. Assume something about your relation, dispersion relation, and you're done. Okay, so all of this was for 1D. Let's generalize it to 3D. It's much easier. Not much easier. It's exactly the same procedure. Why? You say, oh, I have standing waves inside my system. The standing waves are described by some discrete numbers n. I relate those numbers n. I'm going to have, instead of one n, I'm going to have an x, and an y, and an z. Okay, because I have waves in this direction, waves here, waves there. Okay. And the moment that I have this, I count all the different n's. I obtain the total number of standing waves up to a specific threshold. I take a derivative, and I'm going to be done, because over there, it's again going to be some dispersion relation multiplied by a different prefactor. Okay. So let's do it for 3D. Still have time. Questions so far?
Could you repeat what is n prime and k prime?
Yes, yes, yes. So remember, what the goal is. We assume that we have some specific spectrum of omegas. I pick a specific omega, and I want to compute d of omega, the density. Right? How I compute the density? I count the number of states that sits inside this region from 0 up to omega. And I'm saying the total mass of omegas here is omega of omega. Okay? And d of omega is going to be just the derivative, as you do it with mass, with respect to omega. Okay. Now, how to find this total mass of omega? You say for each specific omega, there is a very specific, so you have to count all the number of states of all the different omegas that sits here. And you have an integral from 0 to omega of d omega prime, d omega prime. So all those omega primes that sits inside here, you have to count them. Okay. Now, I don't know how to count omegas, but I know that there is a relation between omega and k. This is a dispersion relation. So I say, well, let's build exactly the same thing for k. Okay. And there's some sort of a density or number of states that live inside here. And in order to find this large omega, I think it's exactly the same number of states that lives here, right? So instead of counting of all the different omega primes, I count all the different k primes that sits between 0 and some k. And for each k prime, there is a specific n prime. Right? Because I know that k is a wave vector. Wave vector have a specific number, 1, 2, 3, 4, 5. Now the specific number is n. So instead of counting from here to 0 from k on k primes, I said, oh, it's exactly the same as for k, there is specific n. Okay? And then there are a bunch of different n primes that are lower than this n. Okay? So instead of, so I want to count this. I say I can count that, and eventually I count this. So I have discrete numbers, and then go and count all those discrete numbers up to a specific n. What is this n? This n is exactly this k, and what is this k? Is exactly my omega. Clear? Yeah. Okay. And we'll do this. We did it for 1D, and we'll do this exactly the same procedure for 3D now. Okay? But the ideology is what I just told you. Look on omegas, instead of omegas, look on k's. Instead of k's, look on n's. For n's, it's easy to count. We know how to count 1 and 2 and 3 and 4 and 5, right? So we'll do this. We'll obtain something about the number of states which sits over here. It's easy. You know this, you know this, you know this, you know that. You take a derivative, you've done. כן, yes.
איך אתה יודע שיחס הדיספרסיה הוא הפיך? מה אם נגיד K שווה אומגה בריבוע?
I have no idea what the dispersion relation is, and I'm going to assume something simple that works. As a good physicist, I worry about problems when I encounter them. Okay? I don't know what the dispersion relation is. I will assume you should see this by now. All those problems, all those models, eventually you want to assume something which is simple enough that you can solve anything at all right? But it gives you predictions that works in nature. So what the Bai did, you usually start with the simplest thing that you can imagine, and then you go on. If it breaks, well, you deal with that. If it does not break, you succeeded. So the dispersion relation, the simplest dispersion relation, which is actually applicable to most materials in nature, is the linear dispersion relation. And this is what we're going to assume. Okay? Don't worry. You can assume crazy dispersion relations that will bring you something different. But the linear dispersion relation works, and this is what we're going to do in a couple of minutes. All right, so what happens in 3D? So in 3D, the idea is exactly the same idea. So instead of vector or number k, it is a k vector, right? So a k vector is kx, x plus ky, y plus kz, z. Each of the constituents, kx, ky, kz, have to satisfy exactly the same boundary conditions. It describes standing waves. So if it describes standing waves, kx is pi divided by L, and ky multiplied by n, and ky is pi, let's call it nx, pi ny divided by L, and kz is pi nz divided by L. So I'm assuming that my three-dimensional thing is a box of L by L by L. Okay, so the volume, I have L, I have L, and I have L. Right? So this is what I have. The vector k is just what? Pi divided by L, and here I have nx, ny, nz. Nx is 1, 2, 3, ny is 1, 2, 3, nz is 1, 2, 3. Don't fall asleep. Now, instead of L, what I know, it's easier to operate this. I know that L multiplied by L is the volume of the system, right? So L to the power 3 is the volume. So the volume, so L is the volume to the power of 1/3. So write down my k vector as pi divided by volume to 1/3 nx, ny, and nz. Okay, now I do exactly the same thing as I've done before, because the ideology is repeated because it's the most important part. Everything else is some math. It's not important. You want to count the number of states from 0 to omega. You don't know how to count it. You go to k. You want to count from 0 to some specific k. You don't know how to count it. You go, you know, oh, there is a integer numbers that represent k. And integer numbers I can count. So instead of counting on k's, I'm counting on n's, and that's easy. So count this, you then know how to count this, and you know how to count that. The same idea applies for nx and y and z. But now, if beforehand we counted in one line, now we're counting in 3 dimensions, right? Because k, in the dispersion relation, k is size and not direction. Okay. Omega of k equals square root of kx squared plus ky squared plus kz squared. So when you want to count all the omegas smaller than omega of k, you need to count all the k primes smaller or equal to k. And let's describe this k in terms of integer numbers, and x and y and z's. Okay. So what do we know from this guy? We know the following. Let's find the size of k. So k, it equals to pi divided by v to the 1/3. And instead of writing it as a vector, we write it as nx squared plus ny squared plus nz squared. And we need to find all the k primes that are going to be lower than k. Which means we need to find all the nx prime squared and ny prime squared and all nz prime such that this guy is b divided by v 1/3 smaller than pi v 1/3 square root of nx squared plus ny squared plus nz squared. Okay, so what is this? This is all the k primes that are smaller than than k. We chose omega, we chose k, we chose nx and y and z, and then we have to count all the different k primes that are smaller than k, which is equivalent to counting on all the integers nx prime, all the integers on 1 and y prime, and all the integers and z primes such that they are smaller than nx and y and z. Okay? So we need to find the number of states, so all possible nx, and all possible ny's, and all possible in z's, such that nx squared plus ny squared plus nz squared smaller or equal, we shall have prime and prime and prime, then a square root of nx squared plus ny squared plus nz squared. Previously, we had one integer number. Now we have 3, so we have much more states over there. Going forward, what I have here, it's a 3-dimensional thing. So we have 3 dimensions. So we know that we have to find an x and y and z that are smaller than some specific number. Okay, so this is an x prime, and y prime, and then z prime. Okay. So in 3 dimension, we're looking on a bunch of points that are somehow situated in space. Okay, and this is actually a 3-dimensional being. And we're saying the following thing. We need to count all the points such that the distance for each and single point that we take into account is smaller than some specific distance over here. Okay. This is just what? This is k multiplied by v to 1/3 divided by pi. So what is the number of points that sits where? All the points, yes? No? Exactly. But not exactly. So it is, we need to take a ball of radius k v to the 3rd divided by pi, but not the whole ball. Okay? So this guy is just 1/8 of the ball, right? You understand why? Just 1/8 of the ball? Exactly, exactly. So we don't count negative nx and negative nz's and negative ny. So think about it in 2 dimensions, it's easier. For example, in 2 dimensions we had nx prime and y prime, and we had a bunch of points that are sitting over here. Okay? And I'm saying I need to count all the points that their distance from the origin is smaller than kv to the third pi. So I'm taking a radius, okay, and this radius is kv to 1/3 divided by pi. Okay. So I need to take here a surface, okay, or the area of the ball, but I don't need all the ball, because all the ball is what? Is including also negative nx primes and negative ny primes. Or do I need anything? Okay. So in order to count the number of points, I can count the volume of the ball with vector kv to the third over pi, okay? And I take only the part where all the integer numbers are positive. Because I'm not interested in taking negative integer numbers, they're not real for me. Okay? Remember, I counted integers, only positive integers, due to the standing waves. So, we reach to the following. Omega of k in 3D is what? It is the volume divided by 8, right, of ball of radius k v 1/3 divided by pi. So what is the volume of a ball with a radius r? Do you remember?
Ask a question.
Yes.
When you use the formula for volume of ball with radius, of this kind of radius, you kind of assume that the points are continuously dense, no?
No, it's I neglected a little bit. I neglected that some variations near the boundary, but they don't have to be dense, because what I'm saying, well, each point contributing an area of 1. Okay, so when I'm counting the total area and I'm saying that each point contributed an area of 1 around it, so the total area is just the total number of points. That's it. Okay, there's some negligence around the boundary, but it's completely we can completely neglect it. Okay, so the volume is 4/3 pi radius to the third. Volume of a ball. So in our case, omega of k is going to be 4/3 pi, whatever stands inside. So this is the radius, which is k v to the 1/3 divided by pi to the third. And we do not use all the integer numbers, just the positive ones. Because of that, we have 1/8. Hooray, hooray! Where it leaves us. Omega of k equals to 4 to 1/6, right? Pi to the third, pi squared, k to the third, and we have the volume. Next thing is, what is d of omega? As we've seen, d of omega is d omega to d omega equals to d omega to dk multiplied to dk to d omega. Okay. We can erase everything, erase our understanding of whatever, we have over here. And we obtain the following nice thing. D of omega. What is the derivative of this with respect to dk? So you have, so all the prefactor. The prefactor is v divided by 6 pi squared is the same. We take the derivative of k to the third with respect to k. So it's 2k squared dk to d omega. Okay. So eventually, d of omega of k equals to the volume divided by 3 pi squared k squared dk to d omega. Because of the 2. Ah! Sorry. 3, 2. Thanks. No, we keep it like this. We keep the volume as volume. Because it's easier to take into account volume and not the linear dimensions. All right. We're almost done. Because it's like in 1D. Eventually, right? You need to know what is k of omega is, or what is omega as a function of k is. The dispersion relation. What is the dispersion relation? We don't know. Because the dispersion relation tells us about the spectrum somehow, and the spectrum is unknown. We need to assume something. Here, Debye understood that everything boils down to what is the dispersion relation. I can obtain everything. I can obtain the density. I can plug it into the integral that we've seen before, etc., etc. Everything from when you know the dispersion relation becomes easy. So what is the dispersion relation? If you go and you can measure dispersion relations. Omega is a function of k. You need only the positive case, but usually they plot because k positive and k negative is exactly the same. You look in nature what the dispersion relations usually look like, because you can measure them. And they usually look like something this, like quite complicated. Right? They're symmetric, but they're quite complicated. And as the question that I was asked before, how do I know that if I have omega of k, I can understand what is k of omega? But even before that, what is the then dispersion relation? It can be a complicated function, and you have to find it, and you have to compute it, etc., etc., etc. So the idea, as I told you, with physicists, is to assume something as simple as possible, but still captures whatever happens in nature. Because you need to describe, it's our religion, we need to describe nature in simple terms. It sometimes does not work, and sometimes this religion breaks down, but this is the basic assumptions in physics. Nature is simple enough, and we need to understand it in simple terms. Question is, what is simple? Yes? But for Debye, this was Debye's idea. He said the following thing. Look, I'm going to assume that my spectrum is linear. Okay? It's going to be linear up to some specific k. Call it kd, kd, which is going to correspond to omega dBy. Omega dBy. And that is going to be 0. And then 0. So this is a spectrum. A v function, very linear, okay, and then nothing. So you've probably seen this in the class of waves. Omega of k equals c, which is the speed of the wave, right? Multiplied by k. So d omega to dk, d omega to dk is just c. The speed of the wave. This is the assumption. It is the assumption of a harmonic or elastic material. Remember? So some sort of elasticity. Some sort the system does something which does not break it completely. There are no breakings of anything, so a bunch of springs. Okay. But this is still not enough for us. Why it's not enough for us? Nothing is enough for us today. And it's not enough because, well, how many waves do you have? So when you think of a wave, usually think of a wave that just oscillates and it have a specific speed, right? So it's oscillating up and down, up and down. But in three-dimensional material, the wave do something else, right? So when you think of the wave, there are longitudinal waves that are, for example, if the wave propagating in this direction, and the wave is oscillating in the direction of propagation. So we can write that there is omega of k with Cl of k. K now describe the oscillations of the wave in the direction of propagation. Okay. Also, you have, when the wave propagating in that direction, you can have oscillations that are perpendicular to the propagation of the wave. Okay? Those called transversal oscillations. Now, if the wave propagating over here, the longitudinal can only have one specific direction because you have a specific direction of propagation. You can have only one type of longitudinal oscillations. But for transversal, it's not true because if this is your direction of propagation, you can oscillate in the perpendicular direction to the propagation like this, and you can oscillate in the perpendicular direction like that. So you have also omega of k, which is c t1, c transversal 1 multiplied by k. You have also omega of k, which you have c transversal 2 multiplied by k. Let's assume that this direction and that direction. What CL we should pick? CL this, CL transversal 1, CL transversal 2, and the answer is you pick up everything, right? You have to pick everything. Why you have to pick everything? Because you counted the number of states, the different omegas. Now there are omegas that corresponds to that waves, there are omegas that corresponds to this waves, and there are omegas that corresponds to that wave. So whatever we have done so far, we need to do 3 times. Don't worry, we won't do it. 1 for those types of waves, longitudinal, and find the number of those longitudinal waves and found their density. We can do that. 1 for the transversal waves in this direction, and another one for transversal waves in that direction. Okay?
אבל אם התחלנו מקפיצים, אז זה בהכרח גל הזה, לא?
No. In 3 dimensions, no. So it's like this and like that and like that. And also whatever. For example, we won't do, I don't know what to do it, but for example, electromagnetic waves, they don't have longitudinal oscillations. They only have transversal oscillations. But springs, they can do this, they can do that, and they can do whatever. As long as you let them. As long as you let them. If you have one-dimensional springs that cannot do this or that, it's only this, and then you're right. But in 3 dimensions, when you allow your masses to go in y, and in x, and in z, then you have to take into account everything. Okay. So now usually, so what we're getting out of this K squared is still K squared. You don't really care about what it, what it is. So you go into this guy and you say, this is my dispersion relation. So the density, instead of just writing one density, I have to sum up of over all the possible densities of all the possible waves, right? So it is going to be d longitudinal of omega plus d transversal 1 of omega plus d transversal 2 of omega. Have to take into account all the possible densities because you count the number of states of whatever omegas that you have. You don't care longitudinal, this one, that one, you don't care. Remember, you need to count eventually for the partition function all the possible waves. All the possible waves, all the possible omegas. Okay, so we use this form we use this form for each and single omega. Omega with CL, omega with C transversal 1, omega with C transversal 2. So you write it down. You write it down as this. So d of omega, this is the full density. It is V divided by 2 pi squared. Now instead of K squared, we sign up here, we take this one. So here, K equals to omega divided by CL. And here, K equals to omega divided by C transversal 1. And here we have K equals to omega divided by C transversal 2. And we substitute it over here. So instead of K squared, we have the first one, omega divided by CL to the second power, and the derivative of dk to d omega is just 1 over CL. Okay, this is that one. This guy, the prefactor is the same. V divided by 2 pi squared. Now, instead of K squared, we have omega by C transversal 1. So it is omega divided by C transversal 1 squared multiplied by 1 over C transversal 1. And the last one. This. It is plus V divided by 2 pi squared omega divided by C transversal 2 squared multiplied by 1 over C transversal 2. Fantastic. So let us write down everything. So we can take prefactor V by 2 pi squared and omega squared out. So d over omega equals to the volume divided by 2 pi squared multiplied by omega squared. And here we have one over C L to the third plus 1 over C transversal 1 to the third plus 1 over C transversal 2 to the third. Now, it's inconvenient to constantly drag this 1 over this plus 1 over that for 1 of this. So I write this down as 3 multiplied by 1 over some C to the third. Some effective velocity. Okay. So this is the final formula. D over omega equals to V by 2 pi squared omega to the second divided by C to the third, and we have a factor of 3 over here. this was the purpose, our goal, to find the density. And this is the density that we found. Now we go back and back and back and back and back where we started. It was a lot of math, a lot of physics in between, a lot of stories about standing waves. Those stories are a little bit different in 1 dimension, 2 dimensions, and 3 dimensions because you have to count this volume. But the story is always the same, the ideology and story. Now, after we've done all of this, and we got very, very, very tired, and it's raining outside, but still, we wanted to compute the free energy. And this free energy was -1 over beta, and summation I goes from 1 to 3n, okay, of what? Of log of z of omega I. And we said, instead we don't know how to count omega i's, we want to use some assumptions, we want to introduce an integration. So this guy goes -1 over beta, and integration, don't know, of log of z of omega I, d omega I. Well, we don't need omega I because we just count over them, d omega. And this is the d omega that we found. Okay, so we succeeded in d omega. And now we have still two unknowns. What is the lower bound of the integral? And what is the higher bound in the integral? And this is related to what omegas you include inside. What is the bound? Let's start with the lower bound of omegas. We used it in a dispersion relation. Remember, we assumed it in a dispersion relation. Dispersion relation, omega, as a function of k, was what? Was 0. It's always started from 0. And it went to a specific kd, omega d. But it was started from 0. This was the assumption of divide. Okay? If we had a specific spectrum where for k equals 0, it won't be 0. Okay, some other oscillations, it will be different. But in our case, it starts from 0. So this is 0. This is the lower integral. What is the the upper bound of the integral? Omega d pi. What omega d pi is, so omega d pi. We don't know what omega d pi is, but we put it in any case, omega d. Okay, so we almost done. Don't worry, eventually we'll have to do this integral, which is a nice integral. Not today, but which is nice integral. But we know almost everything. We know what z's are. Right? They are very similar, I'll show them not today, they are similar to Einstein partition functions. So z's are simple, we've seen them. D omega, we know what it is, we computed it. Lower bound is known, upper bound, we say this is omega d pi. So the last point is, what is omega d pi? What is omega d pi? And here it's not clear because we included a lot of assumptions, but originally it is clear that the total summation is over the whole possible degrees of motion in your system. And since you have n particles, each particle has 3 degrees of motion, this is why you sum up to 3n. Okay? So the number of degrees of motion inside your system is 3n. Okay? Now remember, what was each omega? Each omega described a single harmonic oscillator that is one of those 3n degrees of motion. So what is the total number of allowed omegas? Each omega is 1 degree of motion. The total number of omegas have to be 3n. we know that 3n, total number of degrees of motion. It's also the total number of allowed omegas inside the system, right? You remember this. So what we know, according to our assumption, it's like just computing the whole mass. We know that the whole mass is what? 3n. How we compute mass? We go from 0 to omega dBi. This is the largest omega that we can have inside the system according to dBi.
Or d of omega.
D omega, d omega. Okay? So we have this, and this will describe us what omega dBi is. So let's write it down. n equals to 0 for omega dBi. What we had over here, it's 3 to pi squared volume omega squared c to the third, right? This was our d omega. Okay. D omega. Okay, so we take this integral, so 3n equals to, the integration is 3 by 2 v pi squared c to the third of integral from 0 to omega dBi of omega squared d omega. It equals to 3 by 2 v pi squared c to the third of 1/3 omega dBi to the 3. So omega dBi equals to 3 cancels out, so we have 6n pi squared c to the third divided by volume to the power of 1/3. So we know what omega dBi is. This is done. We know what d of omega, let's write it again, d of omega is 3 by 2 v by pi squared c to the third omega squared. We know what this is, what the lower part. Now we know how to compute it. So the only thing that's left is write down the dependence of the partition functions for single harmonic oscillator. We know how to do it. We've done it for Einstein model. I'll remind you in the next lecture. Plug it over here. And hooray, hooray. What we managed to do, we started with a system with a lot of interacting particles, and after a lot of work, it took us 3 hours up to now, it's already 3 hours. We managed to describe everything as a set of non-interacting particles. Those particles that are no reading particles, they are phonons. It was really hard to find their properties, like their omegas, but we managed to do it. Okay, so in 3 hours, we started from a system of something that looked like an interacting system with a lot of interacting particles. Definitely not as a gas, ideal gas, it's something different. But still, eventually, treated it as an ideal gas without any lot of assumptions. Okay? This is what I told you. Any physical system that we will solve in this class is to take something which looks complicated, looks nasty, looks interacting, and somehow to perform a crazy transformation that will eventually bring us to, oh, it's just like a gas. It's very similar to a gas. Yes, that's well, there you have continuous omegas, etc., but like a gas. How to solve this integral and what we're getting for the heat capacity, right? Is it going as Einstein? Is it not going as Einstein? We'll do next week. Happy Hanukkah. And to who already arrived today, the 3 brave students, thank you all. You get 3 points for your final grade. Yeah. תודה רבה.
Yes, yes, question.
You're not getting 3 points.
No, זאת השאלה.
כן.
אבל בלי קשר, הנחת שם שיש בדיוק 3 מצבים שונים לאומגות.
זה בכמות הדרגות החופש שיש לך במערכת. תודה. רגע, זה
אבל
אני לא
איך
אשמח
שאין
לדעת.
ניוון.
מה? עוד פעם תחזור לשאלה?
מאוד הגיוני שיהיה ניוון.
למה? למה זה הגיוני? למה לא?
לא יודע, זה נראה לי כאילו...
אם אני מניח קשר ליניארי, תחשוב על זה, אני מניח קשר ליניארי, אם זה לא יהיה ליניארי אז יהיה לי ניוון אולי, אבל אם אני מניח קשר ליניארי, ויש לי nx, ny, z, שהם כולם שונים, לא יהיה שום ניוון ככה. אני זורק את זה קצת, כן? אבל לא יהיה. וחוץ מזה, הניוונים האלה באומיגות השומות, אני השתמשתי בהם כדי להכניס את זה ל-D, כן? היו לי 3 D, 1, 2, 3. ספרתי טוב. יכול להיות אתה אומר, אולי יכול להיות ששכחת משהו לספור, אבל אני כן, היה ניוון לגבי כל אומגה, ולכן הכנסתי את זה בפקטור של ה3 שנכנס לתוך ה-D אומגה. הניוון היה, כן, רק בגלים longitudinal and transversal. חוץ מגלים ארוכים ורוחביים, לא היה שום ניוון. כי כל אחד יש לו את הסט מספרים המאוד שונה של המספרים השלמים, שמגדיר את הוקטור גל. ברגע שאני מגדיר את הוקטור גל עם המספרים השלמים האלה, כמו שצריך, אין ניוון. בסדר?
אני לא מדבר על החלק הזה, אלא שסך כל מצבי האומגה הם 3n.
אז טוב, תקפוץ אליי למשרד ונדבר. בסדר?
אוקיי, תודה.
כן. זה משהו שאלה. את זוכרת? מה זה ה-D אומגה? זה כל האומגות האפשריות שאנחנו סופרים. עוד פעם, כשאת חושבת על זה, תנסי תמיד לחשוב על מסה. מסה. האומיגות פה מתארות את האומיגות האפשריות. אני זוכרת, היה לנו המילטוניאן. היה m סכימה מ-i שווה 1 עד 3n של zi בריבוע פלוס אומיגה i בריבוע z דוט zi בריבוע. זה אוסילטורים הורמונים. כל האומיגות האלה פה, הן מתאימות כל אחד לדרגת חופש אחרת. כל אחד לדרגת חופש אחרת. זאת הטענה שלנו. הוא לדוגמה שאל למה יש כל מיני אומגות שהן בדיוק אותו דבר לכל מיני אוסילטור הורמונים. בסדר, נזרוק את זה קצת החוצה, זו שאלה קצת... שאלה נכונה, אבל יותר עמוקה. עכשיו, אני אומר, בסדר, אז מה אני ספרתי? כשאני הגדרתי את ה-D של אומיגה, אז אני צריך לא רק להגיד מהו אומגה הספציפי, בסדר? אני צריך להגיד כמה מצבים חיים, כלומר, אם אני ארשום את הספקטרום של האומיגה, אז הוא רציף. D אומגה אומר את הדבר הבא, קחי אומיגה מסוים, מסביב לאומיגה הזה, בדלטה אומיגה, תחשבי את כמות המצבים שיש כאן. עכשיו, את כמות המצבים שיש כאן, תחלקי בדלטה אומיגה ותשיפי את דלטה אומיגה לאפס. אז כמות המצבים בדלטה אומיגה בחלקי לדלטה אומיגה, בגבול של דלטה אומיגה הולך לאפס, בדיוק הצפיפות. זאת הגדרה של צפיפות. זה D של אומיגה. אז עכשיו, מתוך ההגדרה הזאת, אם אני אקח, אעשה אינטגרציה בין 0 לאומיגה של D אומיגה פריים, D אומיגה פריים, לפי ההגדרה הזאת, אני פשוט אמספר את כמות המצבים שיש לי בין 0 עד לאומיגה, נכון? כי אני סופר, זה ממספר את כמות המצבים, אני עושה אינטגרציה, זה ממספר את כמות המצבים שיש לי. דיבאי אמר, יש גבול עליון לאומיגה, נקרא לו אומיגה דיבאי. מעבר לזה אין מצבים בכלל. אז כל המצבים האפשריים יושבים לי בין 0 לאומיגה דיבאי, וככה אני ממספר אותם. כמה בסך הכל מצבים יש לי? 3. יש לי כל מיני ניוונים, כלומר אומגה אחד ספציפי כן? מתאים ל3, 4, 5, 6, 7 מצבים, זרקתי את זה מהחלון. כי ברגע שאמרתי שיש לי ספקטרום רציף, ברגע שאמרתי את הנקודה הזאת, זה משהו שם, ברגע שאמרתי את הנקודה הזאת, ספקטרום רציף, זה אומר לכל האומגה יש איזשהו מצב. איכשהו אני אולי אכניס מצבים אחרים, כי אני אתייחס לגלים מסוג כזה, וגלים מסוג כזה, והתנודות לסוג כזה, זה משהו אחר, כן? זה הניוון שנכנס פנימה. אבל ברגע שאמרתי יש ספקטרום רציף, כל נקודה מצב אחד, כל נקודה מצב אחד. זה הנחה של ספקטרום רציף. בסדר? אני לא אשכח את השמות שלך, זה הכי חשוב. רק תזכירו לי את זה לקראת הסמסטר, כן? לא להתבייש.
כשאתה מקבל בעצם ביחס דיספרסיה, זה תכלס אומר לך איך הגל מתקדם.
כן, זה אומר שהגלים שלך הם גלים אלסטיים.
אבל אז זה אומר שאתה, אם אתה יודע, נגיד לא תחת ההנחה של קירוב ליניארי, אם אתה אומר שכאילו לא תחת ההנחה של קשר ליניארי, אתה יודע את היחס דיספרסיה, אתה בעצם יודע איך ההפרעה מתקדמת בתוך המדיום, זה אומר שאתה יודע את האינטראקציות, לא?
אתה מניח משהו לגבי אינטראקציות, כן.
אבל אם אני נגיד אמרת שאפשר למדוד את זה גם את היחס דיספרסיה,
כן.
אז אני בעצם יודע מתוך מדידות לדעת, כאילו,
אתה יכול להגיד.
מה האינטראקציות.
כן, כן, כן. אפקטיביות, אינטראקציות אפקטיביות. כי האינטראקציות נורא מסובכות. כשאתה מחשב איזשהו קשר דיספרסיה, אתה הנחת פנימה משהו לגבי זה שיש לי גלים, והגלים נוצרים על ידי כל מיני דברים. בסוף אתה תמדוד איזשהם אינטראקציות אפקטיביות, כאשר, למה אני קורא אפקטיביות? כי יש לך סוג מסוים של אינטראקציות שנותן לך גלים. בסדר? אז עכשיו האינטראקציות האמיתיות הן משהו קצת אחר. אז אתה מדמה כאילו שהם דומים לגלים, לאותם אינטראקציות, עם איזה שהם קבועים. אז את הקבועים האלה אתה תוכל למדוד, אבל זה לא בהכרח אומר שכל האינטראקציות הן רק כאלה, הן דומות לזה. יותר מסובכות, אבל דומות לזה, בקירוב מסוים הם כן.
אבל אז זה אומר שהפונונים הם לאו דווקא בטוחים?
לא, למה?
זה אומר
לא קשור, זה לא קשור, ברגע שרשמת את זה הם בלתי תלויים.
אז מה זה האינטראקציה בין הגלים שהם יוצרים?
הגלים אף פעם לא עושים אינטראקציה בין הגלים.
כי זה מודים כאילו בלתי תלויים.
ברגע שאתה, זה כמו פירוק פוריה, אתה מפרק בפוריה הם כולם בלתי תלויים.
כן,
אבל זה מגיע מפה. ברגע שרשמת את זה בצורה כזאת, האם שינוי של Z2 משפיע על שינוי של Z3? זה היה משפיע אך ורק, כן, אם היה לך פלוס איזשהו קפלינג, נניח Z2, Z1. אם היה לך דבר כזה, אז זה משפיעים אחד על השני. אבל אנחנו לחסנו את הכל, בגלל זה עבדתי קשה כדי ללחסן. כי אז Z1 משתנה, אז Z2 גם יכול להשתנות, והקפלינגס האלה הם משפיעים על האינטראקציה. ברגע שאין לך את זה, אתה יכול להשאיר את Z2 איך שבא לך ולהזיז את Z1, זה לא משנה ולא משפיע.
אז מה המשמעות של אינטראקציות אפקטיביות?
מה?
ומה המשמעות של אינטראקציות האפקטיביות? מה הן?
כי בסוף אני יכול להגיד לך שהחומר הוא כך. זוכר שפיתחתי?
כן, לא, זה אני מסכים.
Ux שווה למינימה, x0 פלוס du ל-dx מסביב לאיזשהו x0, x פחות x0, נכון? פלוס חצי du בריבוע, dx בריבוע, x0, x פחות x0 בריבוע. למה לזרוק את כל שאר הדברים? מותר או לא? פה אני חתכתי את זה, נכון? חתכתי?
אז זה תכלס.
זה האפקטיבי. אני אמרתי, אני אפתח את סדר שני, אני אזרוק את כל שאר הדברים לפח, כי מותר, כי אפשר, כי למה לא, בסדר? ואני השארתי עם איזושהי אינטראקציות, השארתי עם קפיץ, תחשוב על זה. אני התחלתי עם מערכת, ועקרונית בסוף נשארתי עם איזשהו קפיצים, סוג של. לכן זה לא מפתיע שיעשו לי כל מיני פונונים, אוסילציות וכו', כי אני חתכתי את האינטראקציות שלי. האם הן חשובות או לא, זה כבר עניין פיזיקלי. איך אני אבדוק את העניין פיזיקלי? האם התיאוריה שלי מתארת מה שקורה בטבע, ומתארת את זה טוב, אז היה מותר לי לזרוק את זה. אם לא מתארת את זה טוב, אז לא, אתה צריך לקחת את כל השאר הדברים. כן, כי לא לקחת את כל, פונקציה מסובכת בארוכה, לא לקחת את כולה.
כן, אוקיי. תודה רבה.
בבקשה.
אני לא בתפקיד של אחרי כיתה.
רואה? אתה כבר פעמיים או שלוש עושה.
שנה שעברה הייתי ואיכשהו התגלגלתי, לא יודע.
ועוד פעם.
רציתי שיהיה לי מוקלט, אז אני פשוט...
אז תבוא לי יוסי, תגיד, אני עושה את זה, הרי משלמים לכם על זה, נכון?
להם משלמים לי...
נו, אז תראה, אם אתה כל הזמן עושה את זה, תגיד להם שתשלמו לי.
זה קטע מצחיק.
הגלים השונים נובעים מזה שאסור להם להיות באותו מצב אנרגיה?
לא, הם נובעים מכך ש... קודם כל אני הצלחתי לתאר את כל המערכת בעזרת גלים שונים. הם נבעו ממה שעשיתי פה, מתוך הקירוב הזה שעשיתי של הפונקציה של תנודות סביב מינימה, וחתכתי את התנודות עד לסדר שני. אוקיי? מזה נבע יש תיאוריה מתמטית מסביב לזה, אבל תחשבי שברגע שעשיתי את זה, אז בעצם אמרתי יש לי אוסצילטורים הרמוניים פנימה, רק צריך לייצג אותם כמו שצריך. זה הכל. זה הכל נבע מה-X הגדול הזה שציירתי פה. אם הייתי מכניס את שאר הדברים, ולפעמים האפקטים האלה חשובים, מאוד מאוד חשובים, ולפעמים לא. אז זה מאוד מאוד תלוי מה מותר או לא. אז המותר או לא זה נמדד בניסוי בסוף, כי אנחנו בסוף אנחנו מדע אמפירי, כן? זה מאוד כיף לפתח נוסחאות ולשחק איתם, אבל מה אמיתי ומה לא צריך ללכת ולמדוד. אז אם צדקתי או לא צדקתי זה צריך להימדד בתיאוריה, בניסוי. אני יכול להתחיל להגיד, לא, אני צריך לעשות את זה ובתנאי כזה וכזה מותר ובתנאי כזה וכזה אסור. הבעיה שאני לא יכול לחשבן את זה אף פעם. למה? כי אני לא יודע את כל הפונקציה. אני יכול לספר לכם על פונקציה אם יש לי שני חלקיקים. אבל יש לי טונות של חלקיקים שם. המוני חלקיקים, ואני לא יודע מה הפונקציה של כל המשתנים האלה. אני פשוט מניח את זה ומשתמש. עובד? איזה יופי. לא עובד? נתחיל עוד פעם. פיזיקאי תמיד חי באיזשהו רמה של חוסר ודאות לגבי, אנחנו אף פעם לא צודקים באופן מובן, אנחנו מאוד רוצים להציג את זה, אבל בפנים כולם יודעים שזה תיאוריה, זה פחות או יותר, הטבע הרבה יותר מסובך מזה, כשזה עובד זה מצוין, ויום אחד מישהו ישבור את זה וזה לא יעבוד. זה תמיד קורה. יום טוב.
תודה רבה, אסף. עכשיו למכור אותם. כמה משלמים? זה 1,000 שקל לנקודה.
בטח. אני לא מוכרת אותם.
כאילו, כן, לא, אין כאילו, עד כדי כך יקר שאין לזה ערך, כאילו, ערך שאפשר...
זה רק לבוא בגשם.
כן, וזה כאילו, וואו. כן, וואו. ראית? זה יופי, הכל בזכותך. נשבע לך.
שמה, שהגעתי כאילו?
כשאמרת בה, אני לא ידעתי. נשבע לך שמה.
כי הוא כתב במייל ואני כזה,
לא ידעתי.
מה זה גהול, זה זה, אני כזה, מה הוא רוצה? כתוב נייבורי, טוב, נראה לי כל כך...
אני לא ידעתי על זה. אני ישבתי לי בחדר ואני לא יודע, כולי גמור, מסתכל על דברים בפייתון, מעבדה, עניינים, פתאום אני רואה את ההודעה שלך, מה יש הרצאה בזמן, מה הולך פה? אני פותח תמיד, אני רואה את סטס נכנס, ואני מסתכל ככה, אני יושב שם בחדר, אני מסתכל ככה מאחור, אני רואה אותו עומד ככה, איפה כולם?
אני יצאתי מוקדם, אבל היה פקקים כל הדרך, רציתי לכתוב למי שבכיתה, תגיד, תשאלו אותו מה התשובות כמוך.
אין אף אחד, אני באתי, נכנסתי, ואז כולו, וואו, מישהו הגיע. תראי את כל ההחלטה הזה. איזה בוקר, אני באמת לא יודע מה הקטע הכי עצוב, זה שתומר שם.
תומר שם?
ורק אם הוא היה נכנס לפה, הוא מקבל גם נקודות.
כן.